Okay, so before Thanksgiving break, we had dipped our feet into chapter 11. Chapter 11 is about building up some of the language we need in order to talk about probability. Now, probability is going to be concerned with counting, at least for theoretical probability. So everything we did with combinations and permutations and factorials, we are going to be using again. It's going to show up here in probability. In fact, that's the whole reason we even bothered with it in the first place. So probability theory, this is actually some of the most powerful stuff I can ever teach you. Probability theory, think about when you walk into a casino. When you walk into a casino and you play some blackjack, depending on the style of game you play, you have about a 48% chance of winning money in a hand. The casino has about a 52% chance of winning a given hand. Thus, the casino has an edge because while you might walk out and do really well in blackjack that night, some other poor schlup or sap is not going to do as well as you did and probably lose money. And overall, more people are going to lose money to the casino and more money than the casino is going to lose by giving out to players. Thus, the casino pulls a profit. So that's exactly how probability is engineered at a casino. So that's kind of interesting. Probability just shows up everywhere, and we're going to start to see some examples how. So probability must range between 0 and 1 if you express it as a decimal. You'd sit over there. Probability will range from 0 to 1 if you express it as a decimal. And then if you, as a percent, that's obviously 0% to 100%. You can't do better than 100% chance. Even if someone says, I'm going to give it 110%, that doesn't really truly mean anything. It just means they're going to give it their all. But you can't have a 110% chance of getting a blackjack in blackjack or something like that. Obviously, the lowest you can go is 0%. You can't have negative probability. What does a negative 30% chance mean? It means nothing. Now, you might say it to someone who's trying to ask you out, and you're like, there's a negative 1,000% chance I'm going out with you. But that's just kind of a rhetorical way of saying no. So, in truth, probability has to range between 0 and 1. Now, give me one moment. I have to get a student set up to take an exam with me in the classroom. So I will be right back. All righty, sorry about that. Let's get back to it. Looks like you guys are chatting about your breaks. That's fun. Hopefully you had a nice restful break. You'll notice you didn't have any assignments due during the break because I am not evil. But you do have some due this week, it looks like. So just keep that in mind. And let's get back to it. Okay, so again, we just have probability ranges from 0 to 1, things like that. Now we have a few key terms that we need to define. These are basically statistical terms. In fact, chapters 11 and 12 of this course, the last material we cover in this course, is basically a crash course in statistics. So you will always see these terms showed up in statistics, especially experiment. I mean, all of statistics is basically designed to be an experiment or designed around experiments. Now, so an experiment is any occurrence for which the outcome is uncertain. Yeah, you wouldn't run an experiment if you knew what was going to happen. That's not what an experiment is. That's silly. You might have a hypothesis, you might believe you know what's going to happen, but you wouldn't run an experiment if you knew exactly what would occur. That's silly. The sample space of an experiment is the set of all possible outcomes. It's everything that could possibly happen in the experiment. We use a capital S to denote the sample space. Now, if you recall your chapter 2 set theory that we worked on, we used something called U, the universal set. And the sample space then is basically going to replace U, the universal set, in this context. So just keep that in mind. The sample space is basically now the universal set. It's the set of all possible outcomes. You can't have an outcome that is not in the sample space. Now, an event is any subset of the sample space. So think about rolling the dice. If you roll a single die just by itself, and I'll actually write this out with you. If you roll a single die, your sample space is going to be the set, so I use set brackets, of all possible outcomes. A single die only has 6 outcomes. 1, 2, 3, 4, 5, 6, assuming you're rolling a standard die. Now, an event is any subset of that. So let E be the event of rolling an even number. So now E is a subset of that, meaning the things that E itself is going to be a set, and the only things that can come from it are things from the sample space, just like we already know what a subset is from chapter 2. So there you go. That's what E is. It is a subset of the sample space. It's one possible outcome. You could get an even number. That's one possible outcome. Another possible outcome, maybe we'll call it F. You can really call it any capital letter you want. Let's let F be the event of rolling greater than a 4. Greater than a 4. So we can't include 4 itself. It's got to be greater than it. So that's just going to be 5 and 6 and nothing else. This is still a subset of the sample space. Every event will automatically be a subset of the sample space. There's even cooler things we can do with this, real kind of stupid ones. Well, you could use G, I guess, be the event of rolling a 9. What is it? Look at that. Do you see a 9? Can you get a 9 on a single 6-sided die? 9, you cannot. So G is the empty set. That doesn't make any sense here. The empty set, it's impossible to get a 9 in this regard. But remember, we said the empty set is still a subset of the sample space. Way back when we did chapter 2. So G is still an event, and even though it's the empty space set, it's still a subspace or subset. And then finally, you could talk about something like, we could use H. Let H be the event of rolling a 3. So H, it's still a set. The only element in it is the number 3. It's still a subset of the sample space because the elements of H were pulled from the sample space. We use a special definition here. H is said to be a simple event. It has one element only. So a simple event is an event that only has one single outcome in it, no more, no less. So pretty interesting stuff. Pretty interesting. We will see these definitions. Again, this is just kind of basic stuff we're covering at the get-go, Gordon get-go. But back to it, if we were to take all the theoretical outcomes of the sample space, and they may not always be equally likely. In the case of rolling a die, we're going to assume each outcome is equally likely. They each have a 1/6 chance of occurring. But sometimes that may not be the case. Just depends on what you're talking about. So the sum of theoretical probabilities of all possible outcomes is 1, meaning if I add up all the possible outcomes, altogether the probability comes out to exactly 1 or 100%. Again, that shouldn't surprise you. It shouldn't come out to greater than 1. It shouldn't come out to less than 1, or else you've missed something. There's some outcome that's still possible that you haven't accounted for. Ultimately, what we're building toward is something called theoretical probability. Theoretical probability. In theoretical probability, we assume that every outcome of the sample space is equally likely, every individual outcome. But each event is not equally likely to happen as some other event. For instance, the event of rolling an even number, a 2, 4, or a 6. You're more likely to roll an even number than you are to roll a number that's strictly greater than 4. Because there's 3 elements in this set, and there's only 2 elements in this set. You're more likely to roll an even number than you are to roll a 9. In fact, because it's impossible to roll a 9, you are way more likely to roll an even number than a 9. So in the sample space, each one of these individual things is equally likely. You're just as likely to roll a 1 as you are a 2, as you are a 3, as you are a 4, as you are a 5, as you are a 6. But once you're talking about events, some events are more likely than others because they gather different amounts of the sample space together. So ultimately, we're going to use P of E. We're going to use that notation. That means the probability of the event E. So it's a nice shorthand notation. It's just like function notation, f of x, if you've ever used that. But P of E, and it is calculated by counting up the number of outcomes in the event E and dividing by the number of outcomes in the sample space, the total number of possible outcomes. Going back to this example up here, well, we would say that, look at this event E here, it's got 3 of the 6 outcomes, each is equally likely, so the probability of the event E is 3 for the 3 things in E divided by 6 for the 6 things in S, which is 1/2 or 0.5 or 50%. It's just as likely to happen as not happen. You're just as likely to get an even number as you are to not get an even number. The probability of the event F would be 2 of the outcomes are in F out of 6, 2 over 6, which is 1/3. So there's a 33.33333% chance of getting F to occur. The probability of G, will partner, oops, let's use blue. The probability of G is the empty set. There's nothing in the empty set. So it's 0 over 6, which is just 0. So it's a 0% chance that you'll roll a 9, which we already could guess logically. And then finally, 1 outcome in H. So there's a 1/6 chance that you will get the 3, which we already knew that, but it's just kind of an interesting thing to note. So computing theoretical probability, it's nothing more than counting up the number of things in your event of interest that you're trying to calculate its probability and dividing by the number of things possible, the number of things in the sample space. So they stole my dice roll example. Probability of getting a 3 is 1/6. The probability of getting an even number, there's 3 even numbers out of the 6th, so 1/2. A more interesting example involves a deck of cards. A deck of cards. If you know this already, you know that a deck of cards comes with 52 cards in it. In fact, a deck of cards is so important that we need to kind of give it its own little focus here. So if you'll permit me a moment to pull up a deck of cards example. Maybe a nice little graphic of one. Perhaps, Wikipedia, you have never done me wrong. This is a beautiful visual component here that we can use. Now let me share it with you. This is what a standard deck of cards looks like. Sometimes it's called the French deck. I don't know why, but it's just the standard deck of cards that you might use. Of course, if you play blackjack, you would draw from a standard deck of cards, except at casinos, they put 6 decks together. But the only cards you can get are one of these. Poker, of course, uses a standard deck of cards. You don't use the Joker. No. But anyways, this is how a standard deck of cards is broken down. There are what are called 4 suits, and the suit is just the symbol that appears on the card itself. You have clubs, diamonds, hearts, and spades. The clubs and spades then are the black cards, the black suits. The diamonds and hearts then are the red cards, the red suits. Within a given suit here, you have 13 cards. You have the ace, which is sometimes low, sometimes high, depending on the game you're playing. Then you have the numbers 2 through 10. Then you have a jack, queen, and a king. These are called your court cards because you think of a jack, queen, king as being in the court. And so it's pretty straightforward how it works. So there's 13 of each suit times 4 suits. There's 52 playing cards in the deck, in a standard deck. What's really interesting, I think I might have mentioned this last time, but what's really interesting is that if you were to take a 52 card deck and you were to shuffle it really thoroughly, I mean, you can use, there's electronic shufflers, casinos will use them. You could probably buy one for yourself if you're bored and just like watching cards being shuffled. But anyways, if you shuffle a 52 card deck really, 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 really good, well, think about it. How many different ways can you order a 52 card deck? How many different arrangements of it? How many different orderings? Where the top card is one thing, and then the next card is anything else that's random. Well, that would be 52 factorial, right? How many different deck of cards can you create? 52 factorial. Try that out. Try doing 52 factorial in your calculator. Your calculator may not even calculate it. It might give it what is called an overflow error. Your calculator might scream at you and say, does not compute, I don't like that. If your calculator is a little bit newer and powerful, it might do it, but it's going to give you a number that's massive, and it's going to do it in scientific notation using E. So it might be like 3.264 E96. That means 3.264 times 10 to the 96th power, meaning you move the decimal point 96 places to the right in that case. The number is massive. Now, Nicole has done it. Thank you, Nicole. And so 52 factorial comes out to 8.0658 E67, meaning you move the decimal point 67 places to the right. Try that out. Try writing that out on paper. It's ridiculous. It is a massive number. It's more than a trillion. It's a trillion times a trillion times a trillion. I mean, let's see. It would be a trillion 7 times over. Not 7 trillion. I mean a trillion times a trillion times a trillion times a trillion, and then still even a little bit of extra on it. It would be 1,007 trillions. It's such a hilariously massive number. I would bet you $5 that there are less molecules in the entire universe than that number, or that we're in the same ballpark. Think about how many molecules are in the universe. There's trillions of molecules on you yourself. And so the number of molecules in the universe is hilariously massive. And the number of ways you can arrange a 52 card deck is approaching that number. That is ridiculous if you think about it. That's wild. That's huge. What that means is that if you take a 52 card deck and you shuffle it really good, and I mean you use electronic shuffling or good shuffling methods so that it's truly in a random order, there is a very good chance, believe it or not, that there has never been a deck of cards in history on this planet that has been in that exact order that you have it right now. That's ridiculous. That is pretty mind-blowing that you could create something wholly unique like that. It's possible, but it's very unlikely, even in every casino ever on the planet. Even if you were to go 1,000,000 years into the future and playing cards are still used then, I'll bet you $5 you still will have never seen that exact ordering come back to you. So it's an interesting kind of idea, and probability says that. There's a 1 in however massively large that number chance of a deck of cards being randomly in that order. So pretty cool idea. So now going back, we've now discussed what a deck of cards looks like. If you're dealt 1 card from a standard 52 card deck, find the probability of being dealt a king. The probability of a king, well, there's 4 kings in the deck divided by 52 possible cards in the deck. So 4 over 52 reduces to 1 over 13, which is like a 7.69% chance. The probability of drawing a heart, well, there's 13 hearts in the deck out of 52, so there's a 1/4 chance of drawing a heart. Of course, you could also argue there's 4 suits in the deck. The heart is one of them, so there's a 1 in 4 chance that you would draw a heart. So lots of interesting ways that we can talk about this. Now, it turns out that in probability theory, there's 3 principal types of probability. 3 principal types of probability. The first one we just mentioned is theoretical probability, where all we do is we count the number of ways an event can turn out how we like it, and we divide by the number of possible outcomes for the experiment we're running or the sample. So that's theoretical probability, but a theoretical probability calculation is done before the fact. Before the fact. That's huge. We haven't run an actual experiment. So theoretical probability is calculated before the fact. It's called a priori if you want some fancy little, I think it's Latin terms to use to make yourself feel like an academic. What we're talking about is empirical probability, which is after the fact. So empirical probability says you take a probability experiment, however many trials you run it is the denominator. The numerator is going to be the number of times you observe something happening. So in theory, under theoretical probability, if you flip a coin, you would argue there's a 50% chance, a 1/2 chance of getting a heads. It's pretty straightforward and simple. Theoretical probability would make that argument. But let's say you go out and run an experiment where you flip a coin 21 times. 21 times. Well, if you think about it, you couldn't possibly flip heads exactly half the times because you've done it 21 times, which is an odd number. You can't divide it by 2 perfectly. So in empirical probability, you might actually observe 13 heads. 13 heads out of the 21 times you toss the coin. That's going to be a little bit larger than a half. I'll compute it with you. About 0.619 as a decimal. So 61.9%. So even though in theory there's a 50-50 chance of getting heads, that doesn't mean in practice exactly 1/2 of the tosses are going to end up in heads. That doesn't happen in practice. The thought, though, is that if you were to repeat that experiment numerously, you would do it 21 times, you would make your recordings, You do it 21 more times, another 21 times, and you keep doing that over and over and over again, you would eventually average out to being about 50%. If not, then maybe your coin is loaded. Maybe there's something wrong with your coin. So theoretical probability is usually what we're calculating when we talk about probability, but empirical probability is just you can calculate from what you observe. So maybe this is an empirical probability example because what's happening is we have a population. Let's say your population up here, maybe this is the US population or the population of US adults. It says 242, but let's say there's 242 million really. 65 million of the 242 are married males. 40 million are never married males. 10 million are divorced males. 3 million are widowed males. 65 million people in the adult population of the US is a married female, 34 million never married, and so on. So what we're going to do is we're going to select a person at random. We're going to select a person at random from one of these 242 million. Let's find the probability that the person is female. Well, it turns out we're not asking about their status, whether or not they're married, divorced, widowed, or whatnot. We're just saying, hey, how many females are there in the adult population? Oh, 124. How many total are there in the adult population? 242, in this case, million. So we do 124 divided by 242, and about 51% or 0.51 of the adult population in the US is female. So there's about a 0.51 chance that we randomly select a female when we're just selecting any person. I would argue that's theoretically, that's not actually empirical probability. So maybe that's a bad problem, but you would still compute the probability all the same. So we talked about some of the basics of probability just now. We basically add up the number of ways it can go the way we want and divide by the number of ways the experiment can go, whether we like it or not. Now, some of those counting things, some of those are going to be a bit difficult on us. Counting, we may have to use the fundamental counting principle. We may need to use permutations or combinations in order to calculate some of these probabilities that we're going to be doing. So now we're going to bring it all full circle. So 6 joke books or 6 jokes about books. That's a weird word. Okay, I guess these 6 people have given us a joke about books. Okay, it's kind of lame. But anyways, 6 jokes about books by Groucho Marx, famous comedian, Bob Blitzer, never heard of that person, Stephen Wright, I think I've heard of him, Henry Youngman, Jerry Seinfeld, who hasn't heard of Seinfeld, and Phyllis Diller are written on one of 6 cards. The cards are placed in a hat and drawn one at a time. What is the probability that a man's joke will be delivered first and a woman's joke delivered last? So just so you know, Groucho Marx is a man, Bob Blitzer is a man, Stephen, Henry, and Jerry are all men, but then Phyllis Diller is a woman. So what we're doing is we're taking their jokes, we're writing them on these cards. We're going to shake up the hat that we're putting them in. We're going to draw them one at a time, and we want to know what's the probability that we will draw a man's joke first and a woman's joke last, just by random chance. Well, in general, to make this computation, we need to have a denominator, which is going to be the number of ways the experiment can turn out, whether we like it or not. So in this case, there's 6 jokes that could make it as the first one, 5 that can make for the second one. This is clearly a factorial. This is clearly 6 factorial. There's 6 factorial different ways we can pull the jokes out in order. 6 factorial then is 720. So 720 is going to be the denominator of our fraction of our calculation. So the denominator is usually the easy part to get because it's usually just this most straightforward calculation. Now, to figure out what the numerator has to be, the number of ways it can go the way we want. Well, the first joke delivered, we need the first joke to be a man's joke. So there's 5 choices of men that we can put in the first slot here. There's only one choice we can put into the 6th slot because there's only one woman, Phyllis Diller, and that woman, she has to go into the last slot here. So the first slot must be 5, the last slot must be 1. But then everything in between, there's all kinds of different ways we can order those jokes. The second joke has to be delivered by a man if there's only one woman and she has to go last. The third joke has to be delivered by a man. The fourth joke delivered by a man. The fifth joke delivered by a man. So it's going to be 5 times 4 times 3 times 2 times 1, and then times 1 again for Phyllis Diller at the end there. So there's 120 possible permutations that go the way we want. Divided by 720, which is the number of ways the experiment can go whether we like it or not. So it's 120 over 720. We can use our calculator. You can do 120 divided by 720. You can see it'll come out to 0.1666666, where the 6's repeat, which is also just 1/6. And there you go. So that's that probability. On your homework, the problems may want you to basically put your answer either in a fraction, but it may also ask for you to write it as a decimal. So you just need to figure out, convert the fraction to a decimal. You can use your calculator. You might need to convert the decimal to a percent. You know how to do that. So just be sure to read the homework carefully, how it wants you to put your answer in, how many decimal places it wants you to round to, and so on and so forth. Next up, now this one is going to be a little bit tougher, possibly. Powerball is a multi-state lottery played in most U.S. states. So here's what's interesting about Powerball. In fact, here's what's interesting about the lottery. The lottery, in a way, you're kind of gambling. Remember, for the lottery, for the general lottery, you go and you pick some numbers that you think are going to win. You pay for a ticket. You know who profits from the lottery? Is it a corporation? Is it a company? No, the lottery is put on by the government, usually state governments. So the lottery says, well, if we sell $100 million worth of lottery tickets and we only give out an $80 million prize, the state just profited $20 million. But it's just wild to me to realize that you realize the lottery is put on by the state. Even in Texas, where the lottery is, legal and everyone plays it, you can get lottery tickets at any convenience store. In Texas, where gambling is otherwise illegal, the lottery is allowed. It's just kind of weird to you because the lottery kind of is gambling, isn't it? But it's okay if Texas does it, and if the state of Texas profits from this gambling, then great. Maybe that's why Texas has casino gambling illegal. You got to go up to Oklahoma or east to Louisiana to get to a casino. So it's just kind of interesting. Texas will not let anyone else in on their territory. It's kind of like old school mafia guys. They're like, hey, this is our territory, go somewhere else. Anywho, so let's read the problem. It's just a nice big wall of text. Powerball is a multi-state lottery played in most U.S. states. It is the first lottery game to randomly draw numbers from 2 drums. The game is set up so that each player chooses 5 different numbers between 1 and 59. So you first pick a number. You pick 5 numbers. Each of them can be 1 through 59. I believe you can use repeats. You can use the same number twice, but we'll find out. Actually, I believe they may not allow you to use repeats. So you can't use the number 6 twice or something like that. So you pick your first 5 numbers, then you pick an extra number, the Powerball number, which is something between 1 and 35. So twice per week, 5 white balls are drawn randomly from a drum with 59 white balls, numbered 1 to 59. So you can't pick the same number twice, because once a number is drawn from the lottery bin, then it's no longer in there to be drawn a second time. So you can only pick a number one time from between your first 5. Then one red Powerball is drawn separately from a drum with 35 balls, numbered 1 to 35. A player wins the jackpot by matching all 5 numbers drawn from the white balls in any order. So as long as you draw the right 5 balls, it doesn't matter what order you drew them in. And then matching the number on the red Powerball. What is the probability of winning the jackpot if you only buy one ticket and a ticket is $2? What is the probability of winning the jackpot? Well, let's think about it. You have 2 things you have to do here. You have to pick 5 numbers from a pool of 59, and you don't get to use repeated numbers. You don't get to use the same number twice. That is exactly what a combination is. That's exactly what a combination is. So you need to pick the correct 5 numbers from a pool of 59. You don't care, though, about the order of the numbers, because as long as you get those 5 numbers, it doesn't matter what order you got them in, you're on the way to winning the lottery. So you need to do 59 C5. Your calculator can do this heavy lifting. You'll come out to 5,006,386. Now, that's not all you have to do. Not only do you have to pick the correct 5 numbers, you then have to pick the correct Powerball number. There's 35 Powerball numbers. So we need to take the 5,006,386 and multiply it by 35. Multiply it by 35, and you'll end up with 175,223,510. So you have a 1 because you're only buying one ticket. If you were to buy 2 tickets and you made them different numbers on the tickets, don't play the same ticket twice. It's not going to help you. But if you were to buy 2 separate tickets, you'd have a 2 in 175,223,510 chance. If you bought 5,000 tickets, you'd have a 5,000 in 175,223,510 chance. So even if you buy a ton of tickets, your probability doesn't go up. Josh, what if I buy all 175,223,510 possible tickets? Well, there's a few flaws in your plan. First of all, if they're $2 a ticket, that's going to cost you more than $350 million. Well, how many of you have $350 million waiting around? Okay, Josh, well, how come Bill Gates doesn't do it? Oh, well, because it may cost over $350 million to buy all the possible winners, but maybe this lottery is only giving out $120 million. So it doesn't make sense. You're going to lose a lot of money. Even though you will win this lottery, you're going to lose a lot because you paid way more than what the lottery bonus is. Now, way back when, remember when the Powerball was 1.6 billion? There were actually, I think for the first time, there were less than 1.6 billion possible ways or number combinations you could get. Meaning, in theory, you could have bought all the tickets if you have $1.6 billion. You could have bought every possible winning ticket, and maybe it only cost you 1.1 billion to do that. And then you make 1.6 billion, right? So you're profiting 500 million. Not quite. There's a few problems with that. First of all, with the Powerball, when they say they're going to give you 1.6 billion, they're only going to give you that much if you choose to receive it over a period of like 20 years. So you're going to take 1.6 billion, you're going to get monthly payments for 20 years. So maybe you have to divide it by 240 and you'll get that much each month. And then all 240 payments will come out to 1.6 billion. Okay, maybe you're not opposed to that. But here's the other big one. You're going to have to pay huge taxes on that. That 1.6 billion, I don't think the government will let you deduct the 1.1 billion you spent buying all those lottery tickets. So yeah, you might make 1.6 billion, but after taxes, you may only end up with like 900 million, in which case you would have lost money on that bid. So not a good idea to buy them all up. Plus, if anyone else picked the winning number and you did as well, you have to split the pot with them. So yeah, not going to work out for you. That's why you have to look at the lottery like this. You're probably not going to win. If you're going to play it, just do it for fun. Don't spend $1,000 a week on lottery tickets. You're going to lose $950 a week on average, and maybe every once in a while you might win. Ooh, you got $50 here, or ooh, you got $20 here. Don't chase that high of winning. It's not worth it. You can spend way more. But if you're like, hey, the Powerball is 1.6 billion, go down to the convenience store, buy a couple of tickets. You spend $10 or something, and you had a little bit of fun, and you got to talk with all your friends about it, and you watched the number drawings on the news. Hey, maybe you enjoyed that. So you've spent $10 to have a good time. You're not going to win it, but you spent $10 to be a little bit part of the culture. That's fine. I don't think that's a big deal. But don't spend $1,000 a week. Don't spend more, to where you can't afford to eat or pay rent because you have a lottery addiction. Please talk to someone if you have that issue. Okay, next problem. A club consists of 5 men and 7 women. So there's 12 total people in the club. 3 members are selected at random to attend a conference. Find the probability that the selected group consists of 3 men. 3 men. So let's see, we have 12 total people in the club. Now, the number of ways we could choose any 3 people at random. That's going to be the denominator that we want to calculate here in our probability. It's the number of ways that from a group of 12, completely ignoring their gender, from a group of 12, we select any 3 of them. Now, these are just members going to a conference. You don't have a president, a vice president, and a social media correspondent who just posts stuff to Instagram or whatever. No, that's not what's happening. You just have 3 members who are all the same. So this is a combination. We are in combination territory here, folks. So the denominator of our calculation here is just going to be the combination 12C3. That's going to be the number of ways that we can choose any 3 out of the 12 members. And it completely ignores their gender, which is what we want. We are calculating the probability that it'll be 3 men. That's going to be our numerator. So 12C3 will be our denominator. Our numerator, though, we want the probability that the selected group will consist of 3 men. Our numerator needs to be the number of ways we can select 3 men out of 5, and technically 0 women out of 7. So we take the number of ways of selecting 3 men divided by the total number of possible combinations. So there's 220 possible ways we can select 3 people, period. But out of 5 men, we need to do 5C3, which will give us 10. Out of 5 men, there's 10 ways that we can choose any 3 of them. Thus, in total, there's a 10 in 220, which reduces to 1/22 chance that we will choose 3 men at random. Just by, we're far more likely to get at least 1 woman in there, especially because there's more women in this group. So it's very unlikely that if we're choosing at random, we're going to choose all 3 men. But it's a possibility. Okay, let's go ahead and take our break. We'll take our break here. One last thing I want to cover in this section. I want to find the probability that the group consists of 1 man and 2 women. So remember, we have a club of 5 men and 7 women. 3 members are selected at random to attend a conference. Find the probability that the selected group consists of 1 man and 2 women. Exactly 1 man, exactly 2 women. Will remember the denominator of our calculation is just going to be the number of ways we can select any 3 out of the 12. It was 12C3, which, if I remember correctly, was 220. Our numerator, though, this one is going to be a little bit more complex. This one we need to calculate all the ways we can select 1 man out of 5 men and 2 women out of 7 women. All right. Well, that sounds to me like we need to use that fundamental counting principle. We have 2 tasks. I'll use a different color. How about green? We have 2 tasks. Our first task then is to select, not select, but select 1 man out of 5 men. Our next task is to select 2 women out of 7 women. We're going to end up multiplying the number in each of these tasks together. But one extra step, each of these individual tasks is a combination. The number of ways we can select 1 man out of 5, well, it's the combination 5C1, which you may recognize as just the number 5, which is correct. The number of ways we can select 2 women out of 7 is the combination 7C2. Calculate each of those combinations individually, then multiply them. So 5C1 is 5. 7C2, let me see if I can use my math brain, should be 21. 7 times 6 divided by 2, 7 times 3. So we get 5 times 21, which is 105. So the probability, we got the numerator, we got the denominator separately. The probability calculation should come out to 105 over 220. And if you twist my arm, and I don't recommend that you do, but were you to do something as heinous as twist my arm as I buy time here to get my calculator out, 105 divided by 220, you could round it to 3 decimals as 0.477 or 47.7% chance. So if you just randomly select these people, there's a 47.7% chance you'll get exactly 1 man, exactly 2 women. So useful stuff, useful stuff. So now we're going to talk about more probability concepts. We're going to talk about probability involving the word not, involving the word or, and we'll touch on odds, but odds aren't super useful. It's just a different representation of probability. And if you're not going to be gambling much, you probably won't see odds all that much in the real world. So the complement of E, if you remember from chapter 2, we talked about complements in set theory and not, oh, your hair looks nice today. Remember a complement with an E there after the L. It was the event of not being that event. So E complement is the event that E does not happen, that whatever E is. So it's kind of like the opposite. If you remember in logic, we said the complement is like the word not from logic. So if we know the probability of E, we can determine the probability it will not occur. In other words, we can calculate its complement to probability. So the probability that it will not occur is 1 minus the probability it will occur, which kind of just makes perfect sense. If there's a 25% chance something will happen, there's a 100 minus 25 equals 75% chance that it won't happen. 25% chance it will, 75% chance it won't. We're just using 1 because that's the decimal form of 100%. Using the E apostrophe, E complement notation, the probability of E complement is 1 minus the probability of E. And the probability of E is 1 minus the probability of E complement. So it's all pretty straightforward. If you are dealt one card from a standard 52 card deck, find the probability you are not dealt a queen. Well, the probability you will not be getting a queen is 1 minus the probability you will be getting a queen. The probability you'll get a queen is 1 out of 13. There's 4 queens out of 52. 4 over 52 reduces to 1 out of 13. But the probability of not getting a queen, you do 1 minus 1 over 13, you do the math, you'll get 12 out of 13. So an interesting idea. So when you think of complement, you can think of the word not. Think of the word not. Next up, we can talk about something called a mutually exclusive event. 2 events, A and B, are mutually exclusive if it is impossible for them to occur simultaneously. If it's impossible for them to occur simultaneously. So let's think of some mutually exclusive events. Let's say you roll a dice one time, just one time. Let's say you let the event E be the event of rolling an even number. Let's say that F is the event of rolling an odd number. Well, you cannot roll something that is both even and odd. I don't know if you've been told this, but that's not allowed. You can't roll a single number that is both even and odd. So E and F in this case are mutually exclusive. You cannot roll the dice once and get both an even and odd number at the same time. Thus, it's impossible. If you roll the die twice, you're talking about something different. You could get an even on one number and odd on the other. That's possible. But just rolling it once, no. So if you're dealing with 2 events that are mutually exclusive, the probability that one or the other happens, you can just add their individual probabilities. Using set notation, that's the same as saying the probability of A union B is equal to the probability of A plus the probability of B. Only in the case of mutually exclusive events. They can't both happen. So if one card is randomly selected from a deck of cards, what is the probability of selecting a king or a queen? Well, is the event, you're only selecting one card. If you're selecting 2 cards, then it's possible that one card's a king, the other card could be a queen. That's possible. But if you're just selecting one card, it's impossible for you to select a card which is both a queen and a king. It's not impossible for you to select a card which is both an ace and a diamond. So you can cross face value with suits, but you can't have one card have 2 different face values. It doesn't work like that in standard deck of cards. So the probability that you'll draw a king or a queen, you can only draw one or the other. We can just add their individual probabilities. We can do 4 out of 52, the probability of drawing a king, plus 4 out of 52, the probability of drawing a queen. We can just add them. You get 8 out of 52, which is 2 over 13. So it's just as simple as adding their 2 probabilities if you're talking about mutually exclusive events. Oh, what if you aren't talking about mutually exclusive? Ooh. Something fishy is going on when you're talking about mutually exclusive events versus events that are not mutually exclusive. So if A and B are not mutually exclusive, meaning it's possible that they could both happen. So if you're rolling a single die, it's possible that you could roll an even number or a number greater than 3. or rather you can draw an even number and a number greater than 3, because there are even numbers greater than 3. So it's that in that case, those two events are not mutually exclusive. So let's look. Roll a single 6-sided die. We're going to define two events here. E is the event of rolling an even number. Let F be the event of rolling a number greater than 3. These are not mutually exclusive because you can roll a number that is both even and greater than 3. Because think about it. The event E, rolling an even number, 2, 4, and 6. The event F, rolling a number greater than 3, 4, 5, 6. You have some overlap here. You have these and these are overlapping. So they're not mutually exclusive. These events are not mutually exclusive because if I intersect them, I don't get the empty set. In other words, their intersection has something in it. Specifically, E intersect F is the set 4, 6, which is not empty. So if they were mutually exclusive, they would have nothing in common. So for instance, if E was the set of all even numbers, F was the set of all numbers less than 2, there'd only be one thing in F, it's just the number 1, and they have nothing in common. So in that case, they would be mutually exclusive. This is then the probability statement or the probability formula. You are provided it on an exam, but you have to know how it works. Having a formula sheet on an exam almost ties you down, because if you don't know what you're doing, you might get a false sense of confidence because you have a formula sheet. Oh, I can just like pick the formula and like plug it in, right? Maybe you might be able to, but I doubt it. You have to know how the formulas work. And the ironic thing is, you know how they work by doing lots and lots of practice problems. And by the time you've done all those practice problems and you understand how the formulas work and why they work and which one to use, you'll probably just have it memorized anyways. So formula sheet isn't helpful. But we do provide you with one, mostly, hopefully it's good for your anxiety, maybe if you have exam anxiety and you don't stress about it. Anywho, if you have two events that are not mutually exclusive, which is usually going to be the case, it's the more common case I would expect. Well, partner, you're gonna have to use this formula. The probability of A or B occurring is the probability of A plus the probability of B minus the probability of A and B occurring. Using set notation, that's the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersect B. Let's take an example. Let's say you draw one card from a standard, well-shuffled 52 card deck. So the deck is well shuffled, meaning the top card can be any one of those 52 cards in there with equal probability. Let's find the probability that the card will be an ace. Let's make it more fun. Let's make it a jack or a heart. A jack or a heart? Well, let's find this. Notice the key word here is the word or. That's our key word. That tells us we need to use the correct formula. We're going to be adding maybe the probabilities together. We need to determine whether or not they're mutually exclusive. So let's do this. Let's say the event E is the event of drawing a jack. Let's say the event F is the event of drawing a heart. Now, drawing a jack or a heart. Well, let's see. There is a 4 out of 52 chance of drawing a jack. Then maybe I can just add all the hearts in with that, a jack or a heart. So as long as it's at least one of those things, it counts. So there's 13 hearts out of 52. What's the problem with that? The problem is this 4 out of 52 calculation includes the jack of hearts because it's one of the 4 jacks you're counting. This 13 out of 52 calculation also includes the jack of hearts. This includes the jack of hearts. This also includes the jack of hearts. Uh-oh, Chef Boyardee, ravioli. If I add these together, if I just add these together, I will double count the jack of hearts. Oh no. So here's what I'm going to do. I'm going to subtract off the probability of drawing the jack of hearts. We need to subtract off the probability of drawing the jack of hearts. It's still counted once though, which is what we want. It's counted exactly one time. It's counted here and here. We subtracted off, leaving the other one still in play. And you're going to end up with 16 over 52 as your true probability, which reduces to 4 over 13. And then you can have a field day with whatever that is as a decimal or a percent. Well, wait a minute. I had to add them, but then I subtracted something. Wait a minute, Wilbur. This is exactly where the probability formula comes from. The probability of A or B, you can also call it E or F. E or might be your favorite Winnie the Pooh character. You add their individual probabilities, but then don't forget that when you do this and they're not mutually exclusive, you're double counting the number of things that are both E and F as well. So you need to subtract it off once. Minus the probability of E and F. Which is just exactly where this formula came from. Very cool, says I. So we've got a weird animal-themed problem here. In a group of 25 baboons, 18 enjoy grooming their neighbors. Okay. 16 enjoy screeching wildly. Well, all right. Who doesn't enjoy that? You know, who can really just honestly say they've never just screamed wildly for no reason? I can't say that. 10 of them enjoy doing both grooming their neighbors and screaming wildly. If one baboon is selected at random, find the probability that it enjoys grooming its neighbors or screeching wildly. Remember, the word or in math means one or the other or both. It's the and or from English. Since 10 of the baboons enjoy both those things, both grooming their neighbors and screeching wildly, these events are not mutually exclusive. So the probability that they will enjoy grooming their neighbors or screeching wildly, you take the probability they enjoy grooming plus the probability they enjoy screeching. Notice if you add them together, you're going to get more than 25, meaning you're going to get a probability greater than 100%. So that's a nice little fail-safe. You're like, wait a minute, Pilgrim. You're going to get a probability greater than 100%. It's impossible. Don't forget, you need to subtract off the ones who enjoy doing both because you've double counted them. You've counted those 10 here as well as here, so you need to subtract it off once. You do that calculation, you're going to end up with 24 over 25, which is 0.96 or 96%. So 96% of baboons enjoy either grooming or screeching or perhaps both of those things. So if you select one at random, there's a 96% chance you're going to get a baboon that enjoys grooming or screeching or even both of those things. Now, the last thing we're going to talk about odds. Some have said that I'm so good at probability calculations, having a statistics background, they call me the wizard of these things called odds. So the wizard of these odds concepts here. Odds are a little bit weird, a little bit unique. If we know the probability of an event, we can determine the odds in favor or the odds against the event. It's just going to be a ratio of the probability that it can go, the odds in favor of an event. It's just a ratio of the probability that the event occurs to the probability it doesn't occur. So it's like saying, if there's a 5 to 7 chance in favor of me winning a race soon, 5 to 7, well, there's 12 total kind of chances in the state of nature. 5 of them go my way. So a 5 to 7 chance in my favor means I have a 5 over 12 chance of actually winning. That's my actual probability. So it's a ratio of it going your way to it going against you. However, if you were specifically saying the odds against an event, it's a ratio of the number of states that go against you divided by the number of things that go your way. So normally, whenever you see the odds, like the odds the Cowboys will win the Super Bowl, you might see 100 to 1. 100 events or 100 outcomes go against the Cowboys to only one that goes in the Cowboys' favor. Thus, the probability the Cowboys will win the Super Bowl, according to that, is 1 divided by 101, because there's 101 total kind of, I don't know how to put it, chances that go in favor of the Cowboys winning the Super Bowl. Very unlikely this season. It looks like we're not even going to be able to win our meager division. If you watch the Thanksgiving Day blowout at the hands of the Washington Football Club, we were close. We kept it close to the fourth quarter. We were only down 4 points early in the fourth, totally winnable game. And then they did that fake punt call when it was 4th and 10 in our own side of the field when we were only down 4 points. It didn't seem like a prudent call. And they made that call, and we bombed it horribly, and then we gave Washington all the momentum, and they just destroyed us after that. So, yeah. So anywho, let's say you roll a single 6-sided die. Find the odds in favor of rolling a 2. Well, the probability of rolling a 2, there's only a 1/6 chance that you'll roll a 2. The probability against you rolling a 2 is 1 minus 1/6, the probability you do roll 1. So there's a 1/6 chance you roll a 2. There's a 5/6 chance you don't roll a 2. So we do 1/6 divided by 5/6. You're literally doing 1/6 times the reciprocal, 6/5. The sixes cancel out and that reduces to 1/5. But that's not 1/5. Let's read it carefully. That's not 1/5. What it is, the probability of rolling a 2 is not 1/5. It's 1/6. 1/5 really should be read as 1 to 5 odds in favor of rolling a 2. There's one odds or one chance that goes your way, rolling a 2, compared to 5 odds that go against your way. Now, if we wanted to know the odds, say, against the odds against rolling a 2, we actually just flip this on its head. We do 5/6 over 1/6, which would reduce to 5 over 1. So there are 5 to 1 odds against rolling a 2. 5 of the possible chances go against a 2. Only 1 of the possible chances go in favor of a 2. So there's 5 to 1 odds. And so when you read odds, you usually, depends on the site. Sometimes you'll read odds against, sometimes it'll be odds for, and it's really confusing. What's extra confusing is that in England, on their gambling websites, the odds you'll see in England, they tell you the amount of money you'll win in America. In America, when we say there's 2 to 1 odds, what we're saying is there's actually 2 odds against 1 odd in favor of it going the way you're gambling, which means if you bet $1, you should win $2. So for instance, it's not very likely maybe that the Kansas City Chiefs will lose a game. So if Kansas City is playing the Dallas Cowboys, and Kansas City is way better than Dallas, if you decide to bet on the Cowboys, it's a long chance that it's going to happen. It's not very likely. The studio or the casino might give you 6 to 1 odds, meaning that 6 out of 7 chances they think will go the Chiefs' way. 1 chance out of 7 will go the Cowboys' way. So the Cowboys are the underdogs. They're not likely to win. But what the casino will do is they'll, in order to entice you to bet on that, they'll say, but in the unlikely chance that the Cowboys do win, if we're giving you 6 to 1 odds, then we will pay you in winnings 6 times whatever you bet. So if you bet $1 on the Cowboys in that situation, and the Cowboys manage to pull off a win, the casino's not only going to give you your dollar back, they're going to give you $6 extra in winnings for a total of $7. 1 of which was already yours to begin with. 6 is new money you just made. Notice that it's a little bit confusing. You got to differentiate between the profit and the revenue and all that. In England, if you go onto their betting websites, they will say that the Cowboys are 7 to 1 odds in the exact same situation. The 7 is the amount of money you'll get coming back to you, both your winnings and your original bet. And as you can imagine, it's awfully confusing. It's very confusing. So international or English odds or odds from another country may not be the same as we display them in America. So just keep that in mind. And this is not one of those cases where you can just say, well, it's clearly better overseas. America's terrible. No, what are you talking about? Well, why is that better? It's just different. You just have to know the system. So you can convert your odds back to probability. If the odds in favor of an event are A to B, for instance, if the odds in favor of a horse winning are 2 to 5, it's odds in favor. Thus, 2 of the chances go in favor of the horse, 5 of the chances go against the horse. There's 7 total chances, though, which is why we add the 2 and 5, and that's the denominator. The numerator is the number of chances that go our way. So 2 to 5 odds does not mean there's a 2/5 chance the horse will win. 2 to 5 odds means there's actually a 2 out of 7 chance the horse will win, because there's 7 total chances you're talking about. So the probability that the horse will win the race is 2/7. If the odds against the horse were 2 to 5, that means that 2 of the chances go against the horse, 5 of the chances go in favor of the horse. So the horse actually has a 5/7 chance of winning. You just have to read it very carefully. So the odds against, let's change it up. The odds against a particular horse winning are 2 to 5. Well, that changes everything. You can't quite use that formula. Now, if the odds against are 2 to 5, 2 are the odds against, 5 are the odds actually in favor. We're just changing the order of it. Thus, there is actually a 5/7 chance that the horse will win in that case. So it just depends on how you're reading the odds. You have to be very careful with it. Just think about it logically. 3 to 1 odds does not mean there's a 3/1 chance of winning, because 3/1 isn't even a valid probability. That's 3 or 300%. So you have to know really what odds means. Okay, that's going to be it for today.